What we're talking about today is an introduction to gases. This is our next unit. So far, for the most part, all the things that we've talked about or dealt with in a lab kind of situation have been either solids or liquids. Now we're going to spend a few weeks just focusing on gases. This is one of my favorite units to do because there are lots of little fun labs that we get to do. There'll be a couple of them later this week even, and then we're going to do one demonstration kind of mini lab today when you're done with your notes. So we're starting with gases. And we need to lay some groundwork today to start studying gases. And there's one theory that we need to understand in order to be able to describe how gases behave and to be able to do some calculations, of course, with them. That theory is called the kinetic molecular theory. What does kinetic mean? Moving. Usually we describe kinetic energy as energy of motion. So we're talking about moving molecules. There are 4 parts to this theory about moving molecules. And we use this theory to explain the behavior and properties of gases. We use this theory to explain the behavior and properties of gases. There are 4 parts or 4 pieces of information that go along with this theory, and each of them has to do with molecules that are moving. Part 1 of this theory says that we can assume that particles of a gas are in constant random motion. Particles of a gas are in constant random motion. Molecules are always moving. They're always moving in different directions. Random motion, each molecule in a different direction. However, they can't change direction until they hit something. So all molecules would move in a straight line until they collide with another molecule or maybe the sides of the container that you have them in. One thing that we need to understand about gases is that they can exert a pressure on a container, just like you would fill up your tires with air to a certain pressure. That pressure is caused by the molecules colliding with the walls of the container. Part 2. Particles of a gas are so small compared to the distance between them that their volume is negligible. What does negligible mean? What's it sound like? To neglect. What does that mean? To leave it alone or to ignore it. So, particles of a gas are so small compared to the distance between them that their volume or their size, the size of the actual molecule is so small compared to the distance between them that we can ignore it. We can assume that these molecules don't take up space, or that they take up so little space compared to how far apart they are that it doesn't really matter. Their volume is so small compared to how far apart they are that we ignore it. We assume that their volume is 0. We know in real life that molecules take up space. We're used to dealing with solids and liquids that are made out of molecules, and it's pretty easy to think about how those molecules must take up space. When we're dealing with a gas, the molecules are so far apart, it doesn't really matter that the molecules themselves take up space. The distances between the molecules are so great, we can ignore the size of the molecule itself. Part 3. Molecules are assumed to exert no forces on each other than collisions. Molecules are assumed to exert no forces on each other than collisions. If they collide, if they hit together, there's going to be some kind of force that they exert on each other, just like if 2 people were to run into each other. But the things that we talked about with solids and liquids, intermolecular forces, such as London forces, dipole forces, hydrogen bonds. We compared those to magnets, either attracting or repelling. Those attractions or repulsions are so little because the atoms are so far apart that we don't have to worry about those. Attractions or repulsions are negligible. We can ignore them because the molecules are so far apart. Gas molecules have very great intermolecular distances. They are very far apart. So we can assume that any attractions or repulsions they might have are going to be so small that they don't matter. If you think about holding two magnets really far apart, even if those two magnets do attract each other, you can't feel it if you hold them far enough apart. Part 4. The average kinetic energy, and we abbreviate KE, of particles is proportional to the temperature. The average kinetic energy is proportional to the temperature. What's proportional mean? Is it the same as equal?
No.
Not quite, but it's close, right? Proportional means that those two things kind of depend on each other, or they would change together. So if you increase the temperature, you're going to increase the kinetic energy of the molecules. What's kinetic energy again? Energy of moving, motion. So if you're making the temperature go up, you make the kinetic energy go up. What does that tell you about the motion of your molecules?
They'll go faster.
More or faster. Very good. One side note. Not all particles of a gas have the same kinetic energy. Even if we would measure the gas in a balloon and we would say that it's all at the same temperature, that doesn't necessarily mean that all the particles have the same kinetic energy. When we compare kinetic energy to temperature, we take the average kinetic energy. So some molecules might be a little faster, some molecules might be a little slower. When we compare it to temperature, we take the average. All right, so those 4 parts, the kinetic molecular theory, lay the groundwork for studying gases. The other pieces of information we need to know are the 4 gas law variables, or the 4 things that we can change and observe. So if you turn the page, there's a table to fill out. Your table looks a little bit different than my PowerPoint. I'm still like bullet points. So I'll try to help you figure out what goes in what box. The first gas law variable is temperature. So in the variable box, fill in the word temperature. Then we have a place for the symbol. What do you think the symbol for temperature should be? A symbol, like an X.
T.
Oh,
T.
You were wrong.
Capital T. The definition of temperature, we just talked about this in our last part of our theory. Temperature is the average kinetic energy of the particles. So you've got a tiny little box. Average kinetic energy would be the important part of that to get in that box. Temperature measures kinetic energy. The next box says SI unit. That's the System International Units. In other words, what are the science units for temperature? Celsius. But now we have to add a new temperature scale to our list of things to choose from. We're pretty familiar with Celsius and Fahrenheit. The SI unit is actually a temperature scale that's pretty specific to science applications. It's called Kelvin. Symbol for Kelvin is a capital K. It's just another temperature scale. Just like Celsius, just like Fahrenheit, it's another temperature scale. So how do you get in between Kelvin and Celsius? The equation is right there. Make sure you jot that down in your little box. It even rhymes. K equals C plus 273. Does it pertain to this, Paul?
It does.
Okay.
At least I know what Kelvin is, but you don't even use it anymore, do they?
They don't use what?
They don't really, like, the average person doesn't use it anymore, do they?
The average person doesn't use it, no, but scientists use it all the time. Okay, other alternate units include Celsius. You could put Fahrenheit in that box too, but we don't usually use Fahrenheit in science either. Celsius and Fahrenheit go in your alternate unit box. And then standard conditions. Standard conditions are kind of like the conditions that are most common, or the conditions that we live under quite a bit. The temperature standard condition is a little bit lower than what you would be experiencing for the most part in our classroom. 0 degrees Celsius, what temperature is that? 32 Fahrenheit, that's where water freezes. It's a little bit colder than what we work with, but it makes a nice kind of even temperature to use for our standard condition. So 0 Celsius or 273 Kelvin, those would be equivalent temperatures. And those are your standard conditions, 0 and 273. Next variable is pressure. What do you think the symbol for pressure should be?
P.
A P. We just talked about it. What's pressure caused by?
Movement.
Of
Molecule.
molecules. Okay, movement of molecules. We need to be a little more specific. What do they have to collide with?
Each other or the outside wall.
The walls of the container was what we said. Caused by particles colliding with the walls of their container. So your definition should include collisions with the walls. Collisions with the walls. The SI unit for pressure is called the Pascal, named after a scientist. The symbol for that is capital P, little a. Alternate units include the following. KPa, that stands for kilopascals. Millimeters of mercury, that comes from reading a barometer, which we'll talk about in a week or so. Atmospheres. We talked about atmospheres last year in earth science just a little bit. 1 atmosphere is the weight of our Earth's atmosphere pushing on your head. Weight's probably not the best word to use there, but it's how much pressure there's on your head every day from our atmosphere. And torrs, and we'll talk about that in a couple of weeks as well. Torrs and millimeters of mercury are equivalent to each other. So there's a little side note there. You could just connect them with an arrow maybe in your notes. They are the same. Some conversion factors that we need to know. We need to be able to go between units of pressure. So if you've got a little extra space in your units boxes, or maybe off to the side, these are not standard conditions. I guess they are. They are standard conditions too. You could put them in that box as well. 1 atmosphere, 760 millimeters of mercury, and 101.3 kPa. So somewhere between those 2 boxes, you can spread those out.
Is that 1,000?
These can go in their standard conditions box. They are also conversion factors for how you get between units. Third variable is volume. Should be a V. What is volume?
Space inside.
How much space something takes up. So amount of space that a gas takes up. And a little extra information here, it has to be a closed container because if you didn't have a closed container, it would escape and disperse. One other little side note. The volume of a gas is always the same as the amount or the size of the container that it's in. Gases expand to fill whatever container you put them in. That's why everyone knows when we do a lab that smells. because you can smell it up and down the hall. The container would be the entire building and you can smell it everywhere. Gases expand to fill their container. So the volume of the gas is always the volume of the container. The SI unit for volume, these are a little easier. This one's liters. We've heard of that before. Alternate units include milliliters. We're pretty familiar with that too. You may remember from density stuff that you can also represent volume as centimeters cubed or decimeters cubed. Those two units come from the formula for volume of a box. How do you find volume of a box? Length times width times height. So if you had a box that you were measuring in centimeters, centimeters times centimeters times centimeters will give you centimeters cubed. So that's where those come from. Some conversion factors. 1 liter is equal to 1 decimeter cubed, and 1 milliliter is equal to 1 centimeter cubed. But there are no standard conditions. The fourth gas law variable is amount. Nope, not A. The symbol for amount, this one doesn't make as much sense. It's a lowercase n. But one way you might be able to remember that is to think about the n as if it stands for number. Number and amount are kind of the same. How much gas is there? What's the number of moles or the number of grams possibly for how much gas? Moles is your definition. How many moles or how many particles you could also use. It's also the SI unit. When we measure the amount of gas, we will usually be measuring moles. Alternate units include grams or particles, but you'll have to convert them to moles first before you do any calculations with them. Hopefully by now we're pretty familiar with how you convert grams to moles and vice versa. Do you remember how to convert particles to moles? How many things are in a mole?
Is that the Avogadro's number?
Avogadro's number.
3.02, 101.
You're kind of close.
6.
6.02
Oh, that.
times 10 to the 23rd. Yep. And there are no standard conditions for the amount. All right, we've laid all of our groundwork for gases, so we should be ready to start looking at the behavior of gases.